Welcome to the Explainer. If you've ever felt that your Python code is just slow because it's constantly sitting around waiting for something, then you are absolutely in the right place. Today, we're going to demystify asynchrony and turn all that waiting time into a skill that can really boost your career.
So let's talk about a feeling every single developer knows all too well. You run your code and it just stops. It's hanging, waiting for a network request or a database query or maybe a file to load. All that dead time, it's a total performance killer, and it's exactly the problem we're here to solve.
So here's our game plan. First, we're going to pinpoint this waiting game that's slowing our code down. Then we'll meet our async chef. It's a great little analogy to help build an intuitive understanding. After that, we'll break down the core ingredients, see them in action, and cover the essential rulebook before tying it all back to why this is a skill you absolutely must have for your career.
Okay, let's dive right in. The entire issue, really, it boils down to one single concept: blocking code. And all that means is any line of code that forces your entire program to just halt and wait for it to finish before doing anything else.
Just look at the difference here. I mean, it's night and day. On the left, you've got traditional blocking code with time.sleep. It's like a massive traffic jam. Everything just grinds to a halt. The whole program is frozen solid. But on the right, the non-blocking async.sleep is like hitting an open highway. It lets the program pause one little task and immediately switch over to doing other useful work. That right there is the fundamental game changer.
So how in the world does Python pull off this kind of magic? Well, to make it super intuitive, let's just forget about code for a minute and step into a really busy kitchen.
This is our mental model. We've got one single chef, and that chef is our single Python thread. But this isn't just any chef. This chef is an absolute master of efficiency. They don't cook one dish from start to finish while a line of orders piles up. No way. They juggle everything at once.
And that's precisely what Asyncio brings to your code. It's a system of what we call cooperative multitasking, where each part of your program basically says, hey, I'm at a waiting point, so feel free to work on something else for a bit. It's just like our chef putting a dish in the oven and then immediately turning around to chop vegetables for the very next order.
Okay, now let's break this down even farther. To really get how our async chef operates, we need to look at the 4 core ingredients that make this whole kitchen run so incredibly smoothly.
First up is the event loop. The easiest way to think of this is as the kitchen manager. It is the absolute heart of the operation, constantly scanning all the orders, checking what's ready for the next step, and telling the chef exactly what to work on right now.
Next, we've got core routines. A core routine, which you define with async def, is kind of like a recipe. See, just calling the function doesn't actually cook the dish, it just prepares the set of instructions. It's the recipe card, all ready and waiting to be used.
And here it is, the magic word, await. This is the special instruction inside the recipe that tells the chef, hey, this thing needs to simmer for 10 minutes. Go work on another order and just come back when it's done. It's basically the permission slip that allows the whole program to multitask.
And finally, we have the task. A recipe is no good if it's just sitting on the counter. Creating a task is like taking that recipe card, turning it into an official order ticket, and handing it directly to the kitchen manager, our event loop, to get it scheduled and actually running.
All right, we've got our ingredients. Now let's see how our chef puts them all together to handle a real dinner rush. With multiple orders flying in at once.
This really shows the evolution of efficiency. I mean, you could handle orders one by one, finishing one before even starting the next, but man, that is slow. A better way is creating concurrent tasks, but the best approach, the optimal one, is using async.gather. That's like telling the chef, hey, start all these dishes right now and just give me a shout when everything is ready to go. It is by far the fastest and cleanest way to get the job done.
And listen, this isn't just some cute kitchen analogy. This stuff matters for real-world code. When your app needs to pull data from multiple websites or APIs, doing it asynchronously is the difference between your user waiting minutes versus just waiting seconds. It absolutely shines anywhere your code is just waiting for something else to happen.
Okay, so now that we see the incredible power here, it is so critical to understand the rules of the road. Async I/O is a specialized tool, right? It's not some magic bullet you can use for every single problem.
The most important rule is this one right here. Use Asyncio for I/O-bound tasks, things that involve a lot of waiting. Do not use it for CPU-bound tasks, like heavy math or machine learning.
Our chef is amazing at juggling waiting times, but if you give them a task that needs 100% of their focus, well, they can't do anything else. The whole kitchen stops.
Hey, I want to save you some headaches, so here are 3 classic mistakes to watch out for. Forgetting to put await in front of a coroutine means your recipe never even gets cooked. Using a blocking call like time.sleep, that brings the whole kitchen to a screeching halt. And you should only ever have one kitchen manager, so you only call asyncio.run once. Trust me, avoiding these will save you hours of debugging.
So, we've learned the what and the how, but now let's talk about the why. Why is mastering this specific skill so important for your career in tech right now?
The answer is actually pretty simple. The modern tools that are used to build high-performance web services, they demand it. Frameworks like FastAPI and Scenic are literally built from the ground up on Asyncio. So if you want to build fast, scalable backends in Python today, this isn't just optional knowledge, it's a requirement.
And you better believe this stuff is going to be tested in interviews. Being able to confidently walk an interviewer through these concepts, explaining the event loop, or why async is perfect for I/O, it shows a deep, practical understanding that will absolutely set you apart from other candidates. Ultimately, what we've covered today is really a fundamental shift in your mindset as a developer. Asyncio empowers you to move from writing code that just waits to writing code that actually works. It's the key to building the modern, efficient, and high-performance applications that employers are desperately looking for. So really, the only question left is, what are you going to build first?
Hey, so if you're a Python developer and you're really trying to land a backend or a DevOps role, well, this is exactly what you need to hear. Today, we're diving deep into Docker, and trust me, this is the tool that's going to seriously level up your career.
And listen, that's not just some hype, it's the truth. Mastering Docker gives you a huge advantage. Why? Because pretty much every modern Python application you can think of, from web APIs to data pipelines, you name it, they're all deployed using containers. So let's break down exactly how you can make this skill your own.
We've got a really clear roadmap for this. First, we'll talk about why Docker is so essential right now. Then we'll walk through the core workflow, build our very first app, scale it up a bit, and finally, we'll get you prepped for the exact questions you're going to face in a job interview.
All right, first things first. Why is everybody talking about Docker? Why is this showing up as a non-negotiable skill on so many job descriptions these days?
The magic of Docker really is all about consistency. It finally solves that classic frustrating problem of, well, it works on my machine. By bundling up everything your app needs, the code, the pip packages, even the system libraries, into one single portable thing called a container. And this container will run the exact same way on your laptop, your colleague's laptop, or a production server in the cloud. No more surprises.
Now you might be thinking, hey, wait a minute, isn't this what virtual machines do? And you're on the right track, but Docker is just so much more efficient. See, a virtual machine has to bundle an entire guest operating system, which is super heavy and slow. Docker containers, on the other hand, just share the host's operating system kernel, and that makes them incredibly lightweight and ridiculously fast. We're talking starts in seconds, not minutes.
Okay, understanding this core workflow is absolutely crucial. It's a really simple, 3-step process that takes your code from just being a bunch of instructions to a live, running application.
And this analogy here is perfect. Think of it like baking. The Docker file, that's your recipe. It's got all the step-by-step instructions. When you build it, you create an image. That's like a frozen, ready-to-bake snapshot of your application. And finally, when you run that image, you get a container, the actual running process. So it's just recipe, snapshot, process. Super simple when you think about it that way.
All right, that's enough theory for now. Let's get our hands dirty and actually see just how easy it is to containerize a really basic Python application.
We're going to start with the simplest possible app you can imagine. A single Python file, let's call it app.py. And all it does is print a simple hello message. This is the piece of code we're going to package up.
Next up, we create our recipe, the Docker file. So let's break this down. First, from Python 3.12 Slim tells Docker, hey, start with this lightweight official Python environment. Then, workdir app just creates a folder inside our container for our code. Copy app.py does exactly what it says. It copies our script into that folder. And finally, cmd tells the container what to do when it starts up. In our case, just run our Python script.
So, with those 2 files in place, we just run 2 commands in our terminal. First, docker build, that creates the image from our Docker file. Second, docker run, that starts a container from that image. And there you have it, you'll see the output right on your screen. hello from Dockerized Python. Okay, but what if we go back and change that message in our app.py file, and then we rebuild it? Does Docker have to do all that work again right from scratch?
The answer is a big no. And this right here is a crucial point for interviews. Docker uses a layered file system, and it is incredibly smart about it. Every single instruction in your Docker file creates a layer. When you rebuild, Docker only rebuilds the layers that have actually changed. This is exactly why in real projects, you always copy your requirements.txt file and run pip install before you copy your application code. Your dependencies rarely change, so that slow installation step gets cached, making every single build where you only change your code super fast.
So a single container is great, but let's be honest, real-world apps are way more complex. They usually need a database or maybe a caching service or background workers, and that's where Docker Compose comes into the picture. So the key takeaway here is this. Anytime your application isn't just one single isolated process, you should probably reach for Docker Compose. I mean, if you need a web server talking to a Postgres database, or you need a Redis cache or a Celery worker chugging away in the background, Compose is the tool that lets you define and run all of them together, seamlessly.
And you know what? The configuration for this is surprisingly simple. You just have one file, dockercompose.yaml, and in it you define each part of your app as a service. So here we have a web service that we build from our local Docker file and a DB service that just pulls the official Postgres image straight from Docker Hub. Then, with just one command, Docker Compose up, both containers start up and are automatically networked together. It's that easy. Now, as you start thinking about production, a few best practices become really important. Always use those slim base images to keep the size down and reduce security risks. Swap out the built-in development server for a real production-grade one like Junicorn. Use a .dockerignore file. It works just like .gitignore to keep secrets and junk out of your image. And finally, you'll want to learn about multi-stage builds to create a final image that has only what it needs to run, making it super lean and secure.
So how does all this get you that job? We've gone over the concepts, but now let's laser focus on the interview questions that you are very likely to be asked.
This is the classic #1 question, and you already know the answer. The image is the blueprint, right? It's the frozen snapshot. The container is the running instance of that image. It's the recipe versus the actual cake.
Here's another really common one, and you can mention a bunch of things we just talked about, using slim base images, using a dockerignore file to exclude stuff, and for bonus points, definitely mention advanced techniques like multi-stage builds.
And here's the third question that's almost guaranteed to come up. Docker Compose is a tool for defining and running multi-container applications, and you use it whenever your app is made up of multiple services, like a web server and a database, that need to run and talk to each other.
Okay, so how do you put all this together to really impress a recruiter? Here's your action plan. Build a project that shows you get the modern stack, something like a fast API web app with a Postgres database. Then, show you can handle complexity. Add Redis for caching and a Celery worker for background tasks. Tying it all together with a clean Docker Compose file and putting that project on GitHub, that shows you can build and manage a complete real-world application. That's the kind of portfolio that gets you noticed.
And let's just end where we started. This isn't just about learning a new tool. Seriously, mastering Docker and Compose fundamentally changes how you're seen as a developer. It shows you don't just know how to write code, but that you know how to build, package, and deploy real-world, production-grade applications.
You now have the foundation to become a back-end-ready developer. So the only real question left is, where are you going to apply these skills first? Are you going to go containerize one of your old projects, or maybe start building that awesome portfolio piece we just outlined? The next step is all yours.
All right, let's dive right in. Today, we're talking about one of the most critical skills you need to land that first Python job, Git and GitHub. And let me be clear, this isn't some nice to have on your resume, it's a fundamental requirement. So let's get you job ready.
I mean, that's the goal, right? Well, you're in exactly the right place. What we're covering today isn't just a bunch of theory. It's the actual bridge that will connect the skills you have right now to that first real job offer.
And look, I'm not exaggerating here. Whether you're aiming for back-end development, data science, or automation, knowing Git and GitHub is the absolute baseline. They just expect you to know it. Think of it as your passport into the world of professional coding.
So, here's our game plan. We're going to start with why this is so critical. Then we'll clear up that classic Git versus GitHub confusion. After that, we'll get into the essential commands and the professional workflow you'll use every day.
And finally, we'll tie it all together to build an impressive portfolio and get you ready to absolutely nail the interview.
First up, let's talk about why this is the one skill you absolutely cannot afford to skip if you're serious about a career in this field.
So at its heart, Git is what's called a version control system. You know, you end up with files like project_final and then project_final_ for real? Yeah, Git is the professional way to stop doing that forever. It's basically a time machine for your code. It lets you rewind to any previous version, which is just incredibly powerful for undoing mistakes or even just experimenting without fear.
All right, let's tackle the #1 thing that trips up beginners. It's a really simple difference, but it's so important to get it right from the start.
Here's the simplest way to think about it. Git is the tool on your computer that tracks all your changes. GitHub is the website, the platform, where you upload your projects to store them online, share them, and work with other people. So Git is the artist's toolkit. GitHub is the online gallery where you show off your work.
Now, before we even talk about commands, you need to understand the mental model behind Git. I promise, once you get how it thinks, all the commands just click into place and suddenly make perfect sense.
Everything starts with the repository, or as everyone calls it, the repo. It's really just your project's main folder. When you run Git in there, it creates this hidden .git folder, and that little folder is the entire brain of your project. It's a mini database that tracks every single change you ever make.
Okay, next up is a concept that's a little weird at first, but it's crucial: the staging area. So before you create a save point, you have to tell Git exactly which changes you want to include. Think of the staging area like a shopping cart. You use the git add command to put specific changes into the cart before you head to the checkout.
And that checkout is the commit. A commit is the actual save point. It's a permanent snapshot of everything that was in your staging area at that exact moment. And each one is stamped with a unique ID, who made it, when they made it, and a message explaining what changed.
So when you put it all together, you get this fundamental workflow that you'll do, dozens of times a day. First, you do your work. You modify your files. Second, you stage the specific changes you want to save. And third, you commit those staged changes, creating that permanent snapshot in your history. Work, stage, commit. That's the rhythm of a developer.
Okay, that's awesome for working by yourself, but let's be real, coding is a team sport. So let's look at how this scales up for teamwork. This is the exact workflow used in pretty much every tech company on the planet.
And the absolute key to collaboration is a concept called branching. This is huge. If there's one thing you need to know for job interviews, it's this. A branch is basically a copy of your project where you can work in total isolation. It's like creating an alternate timeline to build a new feature or fix a bug without messing up the main stable version of the code.
This all leads us to the pull request, the heart of modern software collaboration. Here's how it works. You create your own branch, you do your work and make your commits there. Then you push that branch up to GitHub. Then you open a pull request, which is basically you saying, "Hey team, I'm done with my changes. Can you please review them?" Your teammates look at your code, give you feedback, and once everyone's happy, your work gets merged into the main project. That's it.
Okay, so you get the tech, you get the workflow. Now let's talk about the fun part, how to leverage all this to get hired. We're going to turn your GitHub profile into a powerful signal that makes recruiters take notice.
First things first, a critical piece of professional hygiene, the .gitignore file. This is just a text file that tells Git which files to completely ignore. You never want to commit things like your virtual environments or, and this is the most important one, your secret keys and API keys. Pushing secrets to a public repo is a huge, costly rookie mistake, and after this, you're not going to make it.
Next up, your commit messages. Believe it or not, these are a part of your professional resume. Look at the difference here. Vague messages like update or fix stuff, they're useless. A good commit message is specific. It starts with a type like feat for a new feature or fix for a bug fix, and then clearly says what was done. This shows an interviewer that you communicate like a pro.
And finally, let's put it all together and get you ready for that technical interview. Seriously, if you can confidently explain these next few concepts, you are going to be in a fantastic position.
Okay, here's a classic advanced question. What's the difference between git merge and git rebase? Here's the short version. Merge is straightforward. It takes two histories and ties them together with a new merge commit. It keeps the history exactly as it happened. Rebase, on the other hand, rewrites history. It takes your changes and replays them on top of another branch to create a cleaner, straight-line history. Knowing the difference shows a much deeper understanding of Git.
Now, this question isn't about a definition, it's about process. They want to know, can you actually do the work? Can you clearly explain that step-by-step process we just talked about? Creating a branch, pushing your code, opening the PR, getting a review, and merging. If you can walk them through that, it proves you're ready to contribute to a real-world team.
And for the real deep dive question, they might ask something like this. What's really happening when you run git commit? A killer answer here would mention that Git isn't just saving the difference. It's actually taking a complete snapshot of all your tracked files. It bundles them up, gives that snapshot a unique ID or hash, and then links it back to the previous commit, forming that unbreakable chain of history. Answering like that shows you don't just use the tool, you truly understand it.
And I want to leave you with this because it is the absolute truth. You don't have to be some algorithm wizard. But if your GitHub profile shows that you use version control like a professional, with clean repositories, clear commits, and consistent activity, recruiters will take you seriously. It's solid proof that you can hit the ground running from day one.
So here's your challenge. Don't just watch this, do this. Your mission for this week is to get 3 of your best, most serious projects pushed up to GitHub. Use branches, write professional commit messages, create a great README file for each. This is where your new career really begins. Your career starts now. Go for it.
All right, let's jump right in. Today, we're talking about the thing that really separates amateur coders from the pros: data structures and algorithms. You'll hear it called DSA. Now, this isn't just some boring theory, okay? This is the secret weapon for writing Python code that's not just clean, but incredibly fast and professional. So why is this such a big deal? You know that feeling, right? When you're using an app and everything is just instant. It's snappy, it's responsive. And then there's the other side of the coin, that frustrating, endless buffering wheel. Well, more often than not, the difference between those two experiences comes down to exactly what we're talking about today. The secret is all in how the data is being managed behind the scenes. So, here's our game plan. We're going to start with why DSA is every programmer's secret weapon. Then, we'll check out the awesome power tools Python gives you right out of the box. After that, we'll see what happens when you need to build some specialist gear. We'll also cover the instruction manuals, the algorithms, and finally, the most important part, how to choose the right tool for the right job. Okay, first things first, the secret weapon. Before we can start using it, we've got to understand what it is. So, what is a data structure, really? Think of it this way. You wouldn't store soup in a filing cabinet, right? Or keep important documents in a bucket. It just doesn't make sense. Every single piece of data you work with needs the right kind of container. And that's all a data structure is. It's the container. And the container you choose has a massive impact on your program's speed and how much memory it eats up. If you pick the right one, your code is going to fly. Pick the wrong one, and, well, you're basically building in that frustrating lag from the very start. Now, one of the best things about Python is that it comes with this incredible set of tools already built in. Seriously, these are your daily drivers, the Swiss Army knives that you're going to find yourself using for like 90% of the problems you need to solve. First up, the trusty list. This is Python's take on a dynamic array, and its superpower? Getting elements by their position, or their index. You need the 5th item? Boom, it's instantly there. Doesn't matter if the list has 10 items or 10 million. But here's its kryptonite, changing things in the middle. If you try to insert or delete something, every single item after it has to get shifted over. For a huge list, that can be painfully slow. Next, we have the dictionary, which is your absolute go-to for lookups. I mean, it is unbelievably fast. Instead of a number index, you use a unique key to find a value. It's just like looking up a word in a real dictionary to find its definition. And the best part? On average, finding, adding, or removing items is instantaneous. This makes dictionaries insanely efficient for connecting pieces of data. And the hits keep on coming. We've also got tuples. A tuple is basically a list that's been set in stone. It's what we call immutable. Once you create it, you can't change it. This is perfect for data that should never, ever be modified, like a pair of XY coordinates. And then there's the set. A set is obsessed with two things, uniqueness and speed. It automatically throws away any duplicates you try to add, and it can tell you if an item is in the collection almost instantly. It's a powerhouse for membership testing. Okay, but what happens when those standard tools just aren't cutting it, for those really specific, tricky problems? Well, that's when you have to roll up your sleeves and craft your own specialized gear. Let's look at two absolute classics, the stack and the queue. A stack is last in, first out, or LIFO. The best way to picture this is a stack of plates. The last plate you put on top is the first one you take off. This is literally how the undo button works in pretty much every application you use. A queue, on the other hand, is the total opposite. It's first in, first out, or FIFO. Just think of a line at a coffee shop. The first person to get in line is the first person to get coffee. This is crucial for things like managing tasks that need to be done in order. And then we have the linked list. This one's pretty cool. It's a chain of little items called nodes, and each node holds some data and also points to the very next node in the chain. Now remember how we said adding things to the middle of a regular list was super slow? Well, the linked list completely solves that problem. Instead of moving a ton of data around, you just have to rewire a couple of these pointers. It's incredibly efficient for lists that are constantly changing. This is where simple organization becomes a legitimate superpower. A binary search tree arranges data in a hierarchy, and it all follows one beautiful, simple rule. For any given node, everything to its left is smaller, and everything to its right is larger. This simple structure lets you find what you're looking for incredibly fast, because with every single comparison, you could just throw away half of the remaining data. Okay, so we've got our tools, right? We have all these fantastic data structures. But a toolbox full of hammers and wrenches is useless if you don't know how to build anything. That's where algorithms come in. They aren't new tools. They are the instruction manuals, the recipes, the step-by-step guides for actually solving problems with your tools. So let's look at two different ways to find something. A linear search is the most obvious way. You start at the beginning, you look at the first item, then the second, then the third, and so on until you find what you're looking for. It works, but man, is it slow. Then you have binary search. This is the smart way, but it has one requirement. Your data has to be sorted first. It jumps right to the middle, asks, is my target bigger or smaller, and then instantly throws away the half it doesn't need. The difference in speed between these two is just massive. It's not even close. So, since that super fast binary search needs sorted data, we've got to talk about sorting. And here, there's a classic trade-off. You've got simple algorithms like bubble sort that are really easy to understand, but they become crazy slow as your list gets bigger. Then you have the heavy hitters like merge sort and quick sort. They use a clever strategy called divide and conquer. They're a bit more complex for sure, but when you're dealing with huge data sets, they are exponentially faster. And we have to give a shout out to recursion. This is an elegant and really powerful idea where a function solves a problem by calling itself to solve a smaller piece of that exact same problem. I know, it can feel a little bit like Inception at first, but it's the most natural and clean way to work with structures like those trees we were just looking at. So we've got all these different tools, all these different recipes. How in the world do we decide which one is the best for our situation? How can we compare them objectively? Well, we need a common language, a universal measuring stick. And that measuring stick has a name, Big O notation. Now, don't let the formal name scare you. Big O is actually a really simple idea. It's just a way to talk about how well an algorithm scales. It doesn't care about the exact number of seconds it takes to run. Instead, it answers a much more important question. What happens to the performance as the amount of data gets bigger and bigger? Does it stay fast? Does it get a little slower? Or does it just completely grind to a halt? That's what Big O tells us. And this right here, this slide ties everything together. This is your cheat sheet. When you need instant access to something based on its position, you grab a list. When you need to look something up incredibly fast by a unique identifier, a dictionary is your best friend. Constantly adding things to the very front of a sequence, that's a job for linked list. And searching through a massive, sorted collection, a binary search tree is going to be your champion. This is how you start making smart, professional-level decisions in your code. So what's the big takeaway here? What's your path forward? It's actually pretty clear. First, master Python's built-in tools. Get super comfortable with lists, dictionaries, and sets. Honestly, they're going to solve the vast majority of your problems. Then, start digging into the more specialized structures like stacks and trees, especially for things like interviews. Really focus on understanding the core algorithms. And this is the most important part, practice. Build these things yourself, from scratch. That's the moment when it all truly clicks into place. So you see, data structures and algorithms aren't just some abstract topic for a computer science class. They are the fundamental difference between an app that people hate using and one that they love. You've now been handed the blueprints to an incredibly powerful toolkit. You know how to build things that are faster, smarter, and more efficient. So the only question left is, what problem are you going to solve first? All right, let's dive right in. Today, we are tackling a concept that is absolutely fundamental if you're serious about writing Python code, big O notation. If you want to write code that doesn't just work, but works efficiently, especially when things get big, you're in exactly the right place. So let's kick things off with a scenario. I'm pretty sure we've all been here. You write some code, it runs like a dream on your laptop with your little test data set. But the second you push it to the server and it meets real-world data, it slows to a crawl, or worse, just completely crashes. What is going on? Well, the answer comes down to this one simple but incredibly powerful idea. It's not really about the raw speed of your code in a vacuum. The real question, the one that actually matters, is how your code behaves as the amount of data grows. It is all about scale. And if we're going to talk about scaling, we need a shared language, right? For programmers, that language is big O notation. It's pretty much the universal standard for discussing how algorithms are going to hold up under pressure. So what is it really? Well, the formal definition is that big O describes how the runtime, or the number of operations, grows as the input size, which we call n, gets bigger. We're not using a stopwatch to measure seconds here. We're measuring the relationship between the size of the input and the effort required. Let's make that a little more concrete. A great way to think of it is like this. Big O tells you how your algorithm is going to handle its growth spurt, as it gets more and more data to process. Is it going to grow up gracefully, or is it going to get all slow and clumsy? And here is a super important point to remember. Big O is almost always talking about the worst case scenario. It's not about how fast your code could be on a good day with a perfect data set. No, it's about preparing you for the toughest situation your code will face, making sure it won't crumble when it matters most. Okay, so to really get a handle on this, let's picture a ladder. We'll call it the complexity ladder. We're going to start at the very bottom on the most efficient rungs and slowly climb our way up to the ones that we really need to be careful with. Our very first rung, the bottom of the ladder, is the holy grail of efficiency, O of 1, or constant time. This is the dream. It means your code takes the same amount of time to run no matter how big the input is. 10 items, 10 million items, it doesn't care. The effort is constant. And here's a perfect, simple example. This Python function just gets the first element from a list. Think about it. Python knows exactly where the beginning of that list is in memory, so it just grabs it. The length of the list is totally irrelevant. That's a 1 in a nutshell. All right, let's take one step up the ladder to O of n, or linear time. This is super common and pretty intuitive. Here, the runtime grows in direct, predictable proportion to the size of your input. So if you double the amount of data, you can expect it to take roughly double the time. It's a straight line. A classic case for this is finding the largest number in a list that isn't sorted. To be absolutely sure you've found the max, what do you have to do? You've got no choice but to look at every single element. That for loop is your big clue. More elements means more work, 1 to 1. Now we're getting to something really powerful. Rung 3 is O of log n, or logarithmic time. This is a massive leap in efficiency. With logarithmic algorithms, every time you double the input size, you only add about 1 extra step of work. Just 1. Compare that to linear, where doubling the data doubles the work. This is fantastic. The poster child for O of log n is, without a doubt, binary search. Now, the catch is your data has to be sorted. But instead of checking every item, you jump to the middle. If that's not what you're looking for, you instantly rule out half of the entire list. You just keep cutting the problem in half, over and over again. It's incredibly fast on big data sets. Okay, let's just take a quick pause here. This table gives us a great visual recap of the rungs on our ladder. You can really see how the growth rates start to diverge. We've climbed up from the super fast O1 and O log n through the very common ON, and you can see what's coming next. So now we're climbing higher up the ladder, and frankly, it's getting a little dangerous up here. Welcome to ON squared, or quadratic time. This is where the performance of your algorithm can just fall off a cliff if you're not careful. The runtime grows by the square of the input size. The classic sign, the thing you should always be looking for, is a loop inside another loop, where both are iterating over the same data. For every single item I in our list, we have to go through the entire list a second time with j. The workload doesn't just grow, it explodes. And to put a number on that explosion, if your list has just 1,000 items, which isn't very big, this innocent-looking code will perform 1 million operations. If the list has 10,000 items, that's 100 million operations. This is how servers crash. Okay, so we've climbed the theoretical ladder. Now for the most important part. How do we actually apply this knowledge in our day-to-day Python coding? Let's build a practical toolkit. This right here, this is gold. It's a cheat sheet for the big O of common operations on Python's built-in data structures. And I want you to pay very close attention to dictionaries and sets. If you need to check if an item exists in a list, you might have to look at everything. That's O of n. But in a dictionary or a set, it's O of 1, constant time. That is a game-changing difference. So how do you start figuring out the big O of your own code? It's actually a pretty straightforward process. First, just look for loops. They're usually the most dominant part of your algorithm. A single loop often means O of n. Nested loops often mean O of n squared. Next, check the docs for any built-in functions you're using to see their complexity. And finally, remember, we're looking at the big picture, so we ignore constants. O of 2n just simplifies to O of n. Which brings us to our final step, and honestly, the whole point of this. Understanding Big O isn't just about memorizing some formulas to pass an interview, it's about fundamentally changing how you approach writing code. It's about developing a scalability mindset. So, let's nail down the key takeaways. 1. Always remember that Big O is about how your code scales, not its raw speed on a small data set. 2. Learn to spot the dominant parts of your code, usually the loops, because that's what will control the performance. And 3. Know your tools. Leveraging Python's built-ins, especially the O1 nature of dicts and sets, is like a developer's superpower. And so I'll leave you with a challenge. Go look at your own code, one of your own projects. With this knowledge fresh in your mind, I want you to ask yourself, what's the biggest performance bottleneck you can find? And now that you understand the latter, how could you refactor it to be more efficient? Thanks for tuning in.